Okay. The outline of the course and course logistics. Do you have any questions about the course logistics? Anything? The outline and content of the course? Nope. Okay. So today we are going to start with descriptive statistics. And basically just a quick review. Population versus sample. So we usually cannot analyze the whole population. What we do, we take a sample and analyze this sample, which is a subset of population. Okay? And basically, if we have information of population and we want to make some inferences for the sample, then we usually use probability. But if we don't have information about population and we collect a sample, we see the sample, and we want to basically, based on the data that we get from sample, if we want to do some inferences for population, we use the statistics, which what we want to do in this course. Okay. Basically, for descriptive statistics that we are going to cover today, there are two categories: numerical summaries, that when you have a sample of data, okay, you want to use just a few numbers to represent the whole sample. Okay, that's called numerical summaries, and most of you have seen this before. Very simple. And then the other category is graphical summary. We basically cover histogram, box plot, time series plot, a stem and leaf diagram, and if I have time also, we cover basically a scatter diagram. Okay, which using these methods, basically we use a visualization tool to show how the sample look like. Okay, this is very important. Every time that you want to do a statistical analysis, always start with visualization method. Okay, plot as much as you can. If it is time-based plot, just do time series plot. See the histogram. See the distribution, because it gives you some insight. Okay, about the question that you want to answer about using this data. Okay. So, two types of statistics. One is descriptive statistics. As I said, you use a simple set of simple statistical techniques to organize, summarize, display, and describe important features of data. As you can see, this is one example in a manufacturing process. So we use two types of raw material, okay, or plates. One is with a thinner, the other one is thicker, and we want to measure the pull of force after assembly. Okay, so we have two sets of data. We want to measure basically which type of material would be better. So we can simply plot that. So this is pull of force for. This is pull of force for basically the thinner material, and this is for the thicker material. When we plot them, you can see, okay, probably thicker material have, on average, a higher, basically, I don't know if why the cursor doesn't show here. Let's see. Oops. Cannot see the cursor here. Sorry about that. I'm trying to find a way to see the mouse. And extended the screen. Okay. Nope. Okay, good. Thank you very much. So let me see. Okay, now you can see that. So on average, the thicker material has a higher, basically, pull of force. Okay. Another type of basically category of statistical methods are called inferential statistics or inductive statistics, where we have a sample and we do some analysis on sample to make inference for the population. So today, I hope we can finish descriptive statistics. Very simple. Most of you know that. Just a review. And the rest of classes, we just focus on inferential statistics, different techniques on inferential statistics. Okay. Let's start with the numerical summary of data. First, one definition. A statistics is any function of sampled observation. Okay? So let's say you have a population, then you have a sample x1, x2. Let's say this is the length of parts, okay, up to xn. You define a function here, any function. It could be linear function, just simple summation. It could be basically a nonlinear function, multiplication. So any function is called a statistic. Okay? We know that the sample that we observed are random variable because they're coming from a population which has a distribution. Therefore, a statistic which is a function of these random variable, this one is also a random variable. And that's very important because we do lots of inferences later based on these statistics and the property of this random variable. Okay? Okay. Now, some of these statistics are useful for summarizing data. We have a category called central tendency statistics, which show where the data are centered. Okay? Where is the center of data? We have mean. You already know. It's like simple average. You add them up, divided by the sample size. You have median. Median is the place that basically half of data is less than that, or half of data is above that point. Mode is the observation with the highest frequency. We also have variability statistic. So if you have some data, okay, so this is the distribution. The central tendency show that where is the concentration of data. The variability statistics show how wide is the data distributed. Okay, what is the variability of the data? And as you can see, we have range, which is the maximum minus minimum. We have variance, and we have a standard deviation. And I guess you've seen this before, but maybe not under the name of central tendency or variability statistics. Any questions so far? Yes, these are the notations that we're going to use. Okay, so x bar, x tilde, and x hat for the basically sample mean. This is called sample mean, sample median, and sample mode. And the other one is R, S squared, and S. Any other questions? Okay. So sample mean. A simple average. Let me give you one example. Let's say we have 8 observations, okay, from prototype engine connectors, okay. And actually, this is the one that we saw the dot plot for in a couple of slides before. Taking the average, just add them up, divided by 8. If you do that, this is going to be the central tendency or sample average of this particular, the average of this particular sample. Okay? This is important. So we have two basically different concepts. One is population, the other one is sample. Okay? In terms of notation, this is very important. Whenever we are referring to population mean, we are talking about, we show that with mu, okay? Which, as you can see, is all the single observation in the population. We add them up and divide it by capital N. Capital N is the population size, you can see. And a small n is sample size. So this is also notation. Whenever we want to refer to population size, we use capital N. And whenever we want to refer to basically sample size, we use a small n. Okay? And sample mean, which is the average of the sample, we denote it by x bar. The other one we denoted, or population mean, we denote it by mu. In terms of equations, they are very similar, but with different sample, with different n. Okay? And as you know, that most of the time we cannot get the population mean. That's why we use the sample mean to estimate population mean. And you will see in probably next few weeks what are the good properties of X bar in estimating mu. Okay, there are some good properties associated with that. Any questions so far? In terms of notations? Very good? Very good. Sample median, as I said, is a value such that 50% of data are above, or you can say below that point. So how to calculate that? There's a simple procedure. Let me give you one example. So we have these numbers. First of all, we need to sort the data, either in ascending order or descending order. So what is the minimum? You may help me. 12.3. Yes. So 12.3. Then we have 12.6. Another 12.6. What else? We have 12.9. Can you help me? What is the next one? 13.1. 13.5. 4, 5, and 6. So how many data do we have? 8. Okay? So what we do, we want to find the middle. We know that for even numbers, we don't have right middle. So if you have even numbers like 4, you have 2 middle numbers. Okay? So what you do, if it is odd numbers, if the sample size is odd, like 5, this is 5 number, the number in the middle is called median. But if it is even, like 4 or like 8, what we do, we need to find 2 in the middle and take the average. Does it make sense? And that's what basically the procedure says. If n is even number, it's going to be n divided by 2 and n divided by 2 plus 1 plus first number. So in this case would be what? These two numbers, the average of these two would be 13. Okay? Any questions? Simple. Is it too simple? Boring? Okay. Let me see. So sample mode. Observation with the highest, basically, frequency. So in this case, I have these numbers here. Which one is the sample mode? With the highest frequency? Yep. So all other numbers, the frequency of all other numbers is 1. I only have 12.6 with basic frequency of 2. Therefore, I can say my x hat is, which is basically mode 12.6. By the way, this is x tilde, which is sample median. Okay? That's simple. Any questions so far? Go ahead. That was actually a question I wanted to ask you guys. It's good. So what if, let me ask his question. What if we have this, then what is a median? Oh, I'm sorry, what is a mode? That's his question. Very good question. There are 2 modes, exactly. It's called bimodal. Okay? Then you can say we have 2 modes. One is 13.4 and the other one is 12.6. Who answered that? Just want to see. Okay, good. Is it clear? Okay. How about this sample? So actually it's not 11. It's 1, 1, 2, 2, 5, 5, 6, 6. So what are the modes? Mode or modes? M mode or modes? How many modes do we have? 4 modes. Everybody agrees? No, it's not correct. You don't have any modes. Because the distribution is flat. All frequency is the same. So there is no mode. Okay? So that's why we say if the frequency for all observations is the same, there is no mode. Because no one stands out. Does it make sense? Good. Okay. Now, basically, yeah, go ahead.
A 7 at the end, then you'd have 4 modes at that point.
Yeah. And that would be really weird. But yeah, you're right. Go ahead.
Is it possible to not, like, what if you have a bunch of numbers that are really close together but not exactly the same? Can that still be a mode?
No, actually, it depends on the precision of your study and the measurement. Okay? No, they could not be. So what happens if you basically combine them into one category, and instead of basically analyzing the individual numbers, you are analyzing the interval, then yes, that could happen. And that's what we do in histogram. You will see in a few slides. Any other questions? Okay. Now, basically, dispersion or variability statistics or variability summaries. We start with, sample variance and a standard deviation. As you can see, this is the equation. So what it tries to measure basically is the deviation from mean, okay, or deviation from central tendency. We want to see how a spread data is around mean. Does it make sense? Okay. So that's why what we do, we calculate the deviation of each data point. You can see the deviation of each data point from mean. That's one deviation. That's another deviation. Deviation of each data point from mean. And then what we do, we square them and take sort of average divided by n minus 1 in the sample size. Okay. Now question is, why do we do this square? So why we square data? I'm sorry?
Part of negative numbers?
Why do we want to do that?
Because it would throw off all the other calculations.
So in what way? That's true, but in what way?
You're doing the sum, so you'd be adding negative to positive.
And what happens?
They cancel.
Exactly. So the reason is if we do not square that, you can see this is positive, this is negative. Then they cancel out each other. So at the end of the day, this guy, summation of xi minus x bar is going to be 0. So again, this part is negative, this part is positive, this is negative, this is positive. They cancel out each other. At the end of the day, it's going to be 0. Go ahead.
The absolute values?
Exactly. One way is to do a square root. Another way would be to use basically, so one estimator would be this guy. Another estimator would be, oops, the absolute value divided by n or n minus 1. It doesn't really matter. So they have different properties. Okay? They have different properties. They show that this guy, and you will see, I think in next few weeks, have some good properties in terms of estimating the population variance of population. Okay? If you do a square instead of basically just absolute value. However, this guy also has a good property. For example, if one data point, so it's basically robust to outliers. What I mean by that, if you have one, so let's say in this sample, or in this sample, if you have one data point, 35.4, okay? That 35.4 is outlier. They're all close to 13, but one number is outlier. Okay? If you use this one, this is kind of like sort of sensitive to outliers, more sensitive to outliers. Any questions? Okay. What else? this is easier, basically. This equation is easier to calculate, but nowadays we just use computer. It doesn't really matter. And the standard deviation is the square root of s squared. Anybody knows why do we use s? Because we have this guy as s squared, and we define s as a square root of the same thing. Why do we need to define? Both of them have sort of same interpretation, which shows the variability of the data. How spread are the data? So why do we need to define S? Go ahead. Exactly. We want to have the same unit as mean, as original observations, original measurement. For example, if you are talking about, let's say, some length, you are talking about the unit is inch, okay? But here, s squared is a squared data, which is inches squared, and it's the unit of area, not length. In order to get it back to area, then we basically simply use the square root. Does it make sense? Any questions so far? Okay. Here is one example. As you can see, these are original observations. The average is 13. What we do, we calculate the deviation, which is 12.6 minus 13. And then we calculate the square. And we add them up and divide it by n minus 1. This is this number, s squared, and the square root of that gives us the standard deviation. Okay? Any questions?
Why are you dividing it by n minus 1 instead of n? I would guess it's because you don't want to include the mean.
I will answer this question in 2 weeks. So do you remember I told you like there are some good properties for estimator? Okay? If you use n minus 1, you can show that there is a very good property for that estimator for estimating the population variance. Okay? But which is called unbiased estimator, okay? But if you replace n minus 1 with n, then you don't have this property, okay? But I think in a few weeks I'll tell you what biased means and how we can calculate that, and then you will see there that why this estimator is unbiased estimator. But for now, just accept it as is, okay? Any other questions? Nope? Okay. Here is again another set of basically notation. For sample, we use s squared, and this is the equation for that. For population variance, we use sigma squared. Okay? And here is the equation. So there are two changes. So x bar is replaced with mu. Okay? X bar is replaced with mu. Can you see that? And then n minus 1, instead of n minus 1, we use capital N, not minus 1. So basically, if I can see all observations, all population members, then that's the way I calculate the variance. If I don't, that's the way I calculate the sample variance. And that makes sense. You know, if I don't know mu, then I use x bar. Okay? Here, doesn't make sense. Okay? Because I'm using n here, capital N, which is the population size, and here I'm using n minus 1, a small n minus 1, which is the sample size minus 1. And that minus 1 is because of that property I told you. Another simple interpretation is this. Okay. It's also related to something that we learn later. It's called degrees of freedom. Okay? What happens here? So we are using this sample to estimate this mu. You agree? We are using this sample to estimate mu by using x bar. Okay? And again using the same sample to estimate variance. Okay? So since we already estimated mu, we are dropping 1 degree of freedom. So instead of n, we are using n minus 1. That's another explanation. Again, it may not be clear, but down the road we learn more about that. The take-home message for this slide is just a notation. S squared and how to calculate the sample variance, and sigma squared and how to calculate population variance. Any questions? Okay, good. Sample range, just maximum minus minimum. Maximum is 13.6 in this example. Minimum is 12.3. So range is 1.3. That's it. Very simple. Percentiles. But before that, let me just... I forgot to say something which is important. And that's the difference between X bar and X tilde, or sample mean and sample average. So both of them measure sort of central tendency. Do you know where do we prefer to use X tilde over X bar? Or sample median over sample mean? Any ideas? Yep.
If the data is skewed in one direction.
Okay. Close.
If there's an outlier?
If there is an outlier, exactly. So let me give you one example. Just a very simple example. 1, 3, 5, and okay. 1, 3, 5. Let's say, what is the average for this? Is 3. What is the median of this? Is again 3. Okay? What if I change this to 1, 3, 5, and let's say 21. Okay? Then what happens here? What is X bar? Is 7.5. And what is X tilde? Is 4. You can see your median is robust to outlier. So it's closer to the median of the data. However, this guy is going to be very sensitive to outliers. If it is 100, that difference would be much worse. We know that the data are concentrated around 3. Okay? So if you have outlier, it would affect your sample average, but not sample median. Does it make sense? Any questions? Yeah, I mean, one way is to study outliers. When you do and identify the outliers, okay, one way you can do is basically say, okay, why these outliers basically are observed. You need to find the reason. Just kicking out the outliers is not a good idea, because there could be some reason. For example, maybe when you are like talking about a process, maybe something happened at that time to the process and created that outlier. Finding the reason for that is very important for your process improvement. Does it make sense? Okay. Percentiles. Okay. We can have different percentiles from 1 to 100. And here is the basically procedure for estimating percentile. It's very similar to median. First sort the data. Then let's say we are looking for 25th percentile. So your I is 25. Then what you calculate the rank, which is n plus 1 times 25 divided by 100. If this rank is integer, then the ith percentile is the R sorted number. And if it is not, what do? You take the average. Okay? it's similar to what we did in for the median. There are 3 percentiles which are very important for us: 25th, 50th, and 75th. Okay? Do you know what this is? 50th percentile? It's called what? Median. That's exactly median. There are also some quartiles which are important. Quartiles where the first quartile is where 25% of data is below that point. The second quartile is median, and the third quartile is where 25% of data is above this point, okay? Which is exactly the same as 25th, 50th, and 75th percentiles. Does it make sense? Okay. Any questions? Let's see for this example if you want to calculate. Three, four. How many? Three. Had one more. 13.5, I think. Okay. If you want to calculate the percentile, 25th percentile for that, then n is equal to 7. So 7 plus 1 times 25 divided by 100. It's second. That's integer. So it's going to be this guy. So this guy is 25th percentile. Okay? So this is the rank. It means the second data point after sorting them. So that's the first, that's the second. Does it make sense? Any questions? If this guy is not integer, for example, if it is 2.5, then what I do, I select second one and the third one and take the average. Does it make sense? Good. Okay. Now, graphical summaries. These are what we covered was only numerical summaries. Then how we can use some visualization tools to show the data. Okay, we start with histogram. This is the procedure for plotting histogram and drawing histogram. I'll basically skip this procedure, just give you one example. So this example is related to piston rings. So this is the engine. I'm sure you know that. Like the one with a kind of like a engineering background know that actually. So this is the pistons in the engine, and these are the rings, compression rings and oil ring. And the inner diameter is very important for the assembly. So what we do, we take a sample of, which includes 125 observations or 125 piston rings, and we measure the inside diameter. So these are the numbers. This is 125 piston rings. Okay? First step is to find the minimum and maximum. In this case, this is the minimum, and this is the maximum. Okay? Oops. This is the maximum, which is lower bound. For the for the upper bound. For the lower bound, I select a little bit smaller than minimum. If you look at the minimum number here is this guy, 967. Okay, that's the decimal point. But I select 73.965 because I want to have neat intervals. You will see in a minute what I mean by that. So this is the range of data. So my data are distributed in this range. Okay? So the next step is to find the number of bins or intervals, the number of bins or interval that I'm going to use. So it's actually there is a rule of thumb. They said, okay, basically, this is the sample size, the square root of that could be a good number for just the number of bins that you want. In this example, we selected 13. Okay, so This is the range of data. This is 73.965. This is 74.03. Then we want to divide this range into 13 bins. Okay? It's easy, just a simple calculations, and the length of each interval is going to be 0.005. And that's why this is a neat number. It's a kind of a good number. That's why I changed this guy to get this neat number. And then we count. These are the intervals. The first interval, the lower bound is 73.965. The upper bound is 73.970. And then so on and so forth. We have 13 intervals here. And we count the number of observations belong to this interval. Very easy. So that's the frequency. Sometimes we can calculate the relative frequency. What does it show, that relative frequency? Anybody can tell me? So relative frequency means each observation divided by 125. So each frequency. So 1 divided by 125 is 0.08. What is relative frequency?
The concentration of diameters, like what's most frequent in your
That's
sample?
the average. Relative frequency. Look at the numbers. They are between 0 and 1. It's probability. It's sort of like estimation of probability. So it says, if somebody asks, what is, based on the sample that you have, what is the probability of producing a ring with a diameter between this number and this number? Then you will say, okay, that's the probability, 0.008. Okay? And we also can have cumulative relative frequency. Okay? And it can be used for, again, probabilities. But let me ask you this question. What does this number tell me? What is this number telling me?
66% of parts are smaller than that.
Exactly. 66% of parts are smaller than what? 74.05. That's the upper bound, not the lower bound. Okay? For this basically interval. So 66% of data are smaller than the upper bound of this interval. Does it make sense? Very simple, basically, calculations and interpretation. Any questions? Here is the histogram. You can see. Histogram can tell us different things. One is basically shape of data. So you can see this is the shape of data. It's sort of symmetric, okay, for distribution of data. It can show us basically the central tendency, the average, and it can show us the variability of data. Okay, as you can see. Okay, any questions? So this is related to shape. As you can see, this is symmetric. And when you have symmetric, this is a very, very interesting property. If you have symmetric, completely symmetric data, then your x bar and x tilde, or sample mean and median, are exactly the same thing. If your data is right askew, so it means it has a tail on the right side, then your x tilde is smaller than x bar. Okay? And if your data is left skewed, then your x bar is less than x tilde. And that's always true. Okay? Any questions? Good. So another tool is box plot. As you can see, box plot is a tool similar to histogram that show the shape, and also show basically box plots show center, spread, and departure from symmetry. Okay, so let me explain what this box, and sometimes they call it box and whisker. The reason is because of those whiskers here, those lines. Yeah, they call it box and whisker. Anyways, So this guy here, the one and the first end of your box plot or beginning of your box plot is first quartile. Remember Q1, where your 25% of data is less than this point. Okay. This guy here in the middle is median or second quartile, and this guy here is the third quartile or Q3. Okay. And here you have your minimum data point after, not excluding outliers. So your minimum value if you exclude outliers. And this guy is the maximum value when you exclude outliers. Does it make sense? Okay. Now, tell me how this box plot give me information about basically symmetry or shape of distribution. For center, for center and spread is obvious. Why? Because this Q2 or median is a measure of central tendency. And this guy is range. So it's also a measure of basically variation or a spread. How about symmetry? Forget about whiskers. Just focus on box. How can I tell from that box the distribution is symmetric or not? Exactly. If it's evenly spaced, that's simple. So the distance between Q1 and Q2 and Q3 is the same, then basically you have symmetric. So if Q1 and Q2 are close, so if, put it this way, if Q2 minus Q1 is less than Q3 minus Q2, okay, so then what? Anybody can tell me? Is it right skewed or left skewed? Is right skewed, right? Because your distribution is something like this. It has a tail on the right. Okay? If it's the other way around, but Q2 minus Q1 is greater than Q3 minus Q2, then it's left skewed, which is this. Okay? Does it make sense? Actually, it's something like this. This is Q1, this is Q2, and this is Q3. Any questions? Okay. So one thing else that box plot can tell us and can be used is for outlier detection. So you can detect outliers. So as you can see, the numbers outside your basically whiskers are called outliers. How we can detect that? There is basically a simple equation for that. There is something called IQR, or interquartile range. It's actually Q3 minus Q1. Okay? And you define a range. So your lower bound for this range is Q1 minus 1.5, y 1.5. It's kind of like for symmetric distribution that makes sense, but I don't know why, the reason behind that, y 1.5. Q3 minus Q1, or IQR. The upper bound is Q3 plus 1.5. So if your data point is less than this or greater than this, then it's considered as outlier. Okay? This is called outlier detection. Sometimes they replace that. So what it means, the outlier? Outlier means the probability of observing this point from this population is very small. Okay? Why we can say that? Because all the observations that we have are concentrated in some area, but one of them is way out. Okay? Then sometimes they replaced it 1.5 with 3. Okay? And they call it extreme outliers. That's what they call it. I don't know why, but that's what is in your textbook. So it's called extreme outlier if it is more than 3. So this is outlier, this is extreme outlier. Any questions? Okay. One example, this is from a compressive strength data. This is basically from your textbook. Let me show you the data. Data is here. So we have a sample of, I don't know exactly how many. So based on some compressive strength test of 80 specimens. And then this is the box plot for that. As you can see, this is very simple to interpret. First of all, it's symmetric. Can you see that? Q1, Q2, and Q3 are equally spaced. We have a couple of outliers. That's good to know why these outliers are here. And this is the maximum after excluding outliers, and this is the minimum excluding outliers. And as you can see, this is the upper bound for finding outliers, and this is the lower bound for finding outliers. Does it make sense? Okay, again, this guy has nothing to do with this. So this is upper bound for finding outlier. This is the maximum without any outlier. Okay? Not confuse them. Okay, so sometimes what we do, we use box plot to compare different basically situations. So let's say you're talking about that compressive strength. The higher, basically, or in this case, we are talking about 3 different plants, and we want to compare the quality of product of these plants. So what we do, we take a sample from plant 1, we take a sample from plant 2, and we take a sample from plant 3. We plot the box plot, and these are the box plot. It's easy to compare. This plant. So let me ask you this question. If you want to pick one, which one would you pick?
The third one.
The quality index, the higher the better.
Oh.
So you tell them. I should have told you. The higher quality, the better. One, two, three. Again, 3.
One.
3.
So let me see why 3. That's interesting.
Variance is stronger.
That's a very good answer. Okay, but if I'm to pick between 1 and 3, I go with 1. Okay, but my next, because 1 has a much better mean. Even the first quartile, okay, of this guy is greater than the third quartile of this guy. So I could say the whole distribution of plant 1 is better than the whole distribution of plant 3. You agree? Because it's higher than that. However, that's a very good point. If I want to compare 2 and 3 in terms of quality index, which one I would pick? Both of them have the same mean. And you see, like the same median. But we pick 3 because it has a less variability. Okay? Does it make sense? Good. Oh, yeah, sure.
It's the first one and the bottom one is the third quartile.
Yes, exactly. So the box plot I showed you was like horizontal. This one is vertical. Yeah, so this one is Q1, this one is Q3, and this is Q2. Does that make sense? Okay, good. So Friday, I basically finished the descriptive statistics and also used Minitab. I show you how to use Minitab to make these plots. Draw this box plot, time series plot, and other plots, and histogram.